talking about the GCLOCK algorithm and how it is applied within database systems and buffer management. Buffers in database systems are very important because they provide the fastest possible interaction between a database and a CPU. The CPU processes the commands of a database management system and attempts to retrieve data from either the buffer or the relational database, depending on what data is stored on which. So typically, because the buffer is much faster than the hard disk drive on which the relational database is stored, we want the most important or most useful pages of data stored on the buffer. Because the buffer has real capacity limitations, we need to make sure that management of the buffer is efficient to ensure that the database runs optimally. So the solution to this is basically buffer replacement algorithms.
Here are some examples of the best known buffer replacement algorithms. Least recently used. The page that has not been accessed the longest is replaced. This assumes that pages that are frequently accessed in the past few instructions will continue to be accessed frequently in the future few instructions. Least frequently used, here we keep a count of page accesses, and then the page with the lowest count is evicted from the buffer and replaced. And first in, first out. Here we keep track of the pages in a queue. Pages are added at the back of the queue and removed from the front. The clock algorithm is a variant of the LRU replacement algorithm. It stores a circular list of pages in memory. A clock hand iterator points to the oldest page in the list and iterates clockwise over the pages. Each page in the buffer has a reference bit which can be either 0 or 1. Each page's reference bit is initially 1, that is, when it is read into the buffer. When a page is accessed by CPU, its flag is also set to 1. When the clock hand iterates over the pages, the reference bit of each page is set to 0 unless it is being accessed by CPU. When a page is read into the buffer, the first page the clock hand lands on with a 0 reference bit is evicted from the buffer and replaced by the page that has just been read. Here we'll take you through a simple example to help us illustrate the clock algorithm visually. Prior to the buffer being in the state shown here, pages were accessed and added to the buffer in the order A, B, C, and then D. You can see that all the reference bits are initialized to 1, and the clock hand is initially pointing to the oldest page in the list. So we want to access page E from the HDD. The clock hand is pointing to A. The original value of A's reference bit is 1. A's reference bit is then decremented to 0. B's reference bit is decremented to 0. The same goes for C and D. And now the clock hand has returned to page A. Page A's reference bit is currently 0, and so it is removed from the buffer and replaced with page E. Note that E's reference bit is now set to 1. Now the CPU wishes to access page C. Here we can see that page C is already in main memory. Page C's reference bit is incremented to 1. Say we wanted to access page E. The algorithm would simply increment E's reference bit to 1, like this. Now we want to access page Z, which happens to not be loaded in the buffer. Again, we iterate until we find a buffer frame with a 0 reference bit. Page B's reference bit is 0, so we evict it and replace it with page Z, and page Z's reference bit is set to 1.
So the GCLOCK algorithm is essentially the generalized version of the clock algorithm. So it uses the same circular clock structure as the clock algorithm, meaning that when you rotate through pages in the buffer, you rotate clockwise. And it also initializes pages to a value of 1. And by that I mean the reference counter initializes to a value of 1, the same way that the reference bit initializes to a value of 1 for the clock algorithm. Both algorithms both remove pages when the reference counter or reference bit reaches 0, and they differ in the sense that the GCLOCK algorithm uses a reference counter as opposed to a reference bit. So a reference bit can only be 0 or 1, but a reference counter can be 0 to any arbitrary number. Some implementations of the algorithm have a limit for that specific number, for example in the homework, and some don't. But the difference is that in the GCLOCK algorithm, when you access a page that's already in the buffer, you increase the reference counter by 1, no matter what its value is. Whereas in the reference bit, you simply just, when you access the page, you make the reference bit 1. So here is the initial algorithm. So we have an initialized buffer with pages A, B, and C, and D, all of which have a reference counter value of 1. The arrow obviously indicates the clockwise rotation. And the first request we make is for page B. So we rotate only one page clockwise, and we get to B, and we increment it by 1 because we're accessing it, and it's already in the buffer, so the B's reference counter is now 2. For the next one, we'll request D. So that means we have to go through C, and obviously you can see here in the slide, C decreases by 1, it becomes 0, rotate around to D, and it becomes 2, because we have to increment it. The next example, we'll just request E. So E is not actually in the buffer yet, so that means we have to rotate around until we find a particular page that already has a reference counter of 0. So obviously we know that A has a reference counter of 1, so that becomes 0, that doesn't mean we remove it. We go to B, that has a reference counter of 2, so we decrement it to 1. And we go to C, and C already has a reference counter of 0. So that means we can replace C with the E page, and because E is obviously just initializing, then E has a reference counter of 1. So once C is removed from the buffer, it goes back to the relational database on the hard disk drive. And now we'll move on to an example where we use bigger numbers. So here we have the same buffer, and for these particular pages to get sizable reference counts, we would need the CPU to request these same pages from the buffer repeatedly if we were using this algorithm. So let's say the CPU does that, and then as we look on the next slide, we have A reference count of 8, B reference count of 9, E reference count of 9, D reference count of 10. So obviously these aren't that big, but for the purposes of just demonstrating that the algorithm can reach numbers larger than 0 or 1, then this will serve us well. So now just to show that how these big numbers interact with replacing a specific page, we'll introduce the page that we removed, C, and now the algorithm will need to process one of the pages for replacement so that C can fit in the buffer. So in this case, because A has the lowest reference count, we can already tell that after 9 rotations, or 8.5 rotations, it will be the one that is removed with a reference count of 0, and C will replace it with a reference count of 1. So that's just basically a very basic big number example, but that's all we really needed to do, was to show that this particular algorithm can handle bigger numbers than 0 or 1, and that's essentially the difference between it and just the clock algorithm.
In summary, CLOCK and GCLOCK are variants of the least recently used algorithm. They each are a circular list of pages in memory. They both use a clock hand iterator. CLOCK has a reference bit which can take the value of 0 or 1, whereas GCLOCK has a reference counter, which can be 0 or above. Page reference bits are initialized to 1 with both CLOCK and GCLOCK. CLOCK's reference bit, or R, is set to 1 with each CPU access, whereas R is incremented with each access in GCLOCK. R is set to 0 with each non-access iteration in CLOCK, but is decremented until 0 with each non-access iteration in GCLOCK.